So this is the lecture that we'll usually do with engines. Usually a handout that I'll give out in class. So this will be posted onto Canvas where you can download this handout and then you can follow along and fill it out with me. This goes along with chapter 18 out of the book. I'll start by saying that the style of engine that we use in the automotive industry is referred to as an internal combustion engine. We had that conversation back when we talked about chapter 1 and we talked about our 4-stroke cycle, where we have on our intake stroke the pistons moving down and the intake valves open, we're bringing in an air-fuel mixture. The compression stroke, the pistons moving up and the intake valve would be closed, and we'll compress that air-fuel mixture down to a really small volume. Then right towards the end of the compression stroke, both valves are closed. We're going to have ignition take place, or spark, that's going to light that air-fuel mixture, and that air-fuel mixture is going to start to burn just after the piston peaks over top dead center onto the power stroke. Then we have maximum pressure on that piston, and we're pushing down and capturing all of that mechanical energy. Both valves closed on the power stroke. Right towards the end of the power stroke, then the exhaust valve is going to begin to open, relieving the pressure, and as the piston comes up, we're going to push all of the burned air-fuel mixture, exhaust gas, out past that open exhaust valve. Towards the end of the exhaust stroke, the intake valve is going to begin to open. There's a point where the intake and exhaust valves are open briefly for a short period of time. At the same time, that's referred to as valve overlap. And as the exhaust valves are leaving, exhaust gases are leaving. The property of inertia helps us that an object in motion wants to stay in motion. The intake gases and air-fuel mixture, since it was not moving, would want to stay at rest. So as the exhaust valve and the intake valve are open at the same time and those exhaust gases are flowing out of the exhaust valve, it helps to siphon and get the air-fuel mixture moving past that open intake valve. And then as the piston nears top dead center of the exhaust stroke, then we're going to have our intake valve starting to open. As we come down our intake stroke, our exhaust valve will close. And then now that the intake gases are moving, then they're going to be easier to keep moving because of the law of inertia. And then we end up filling the cylinder and have a 4-stroke cycle that starts all over again. The internal combustion engines that we use will run on a variety of different fuels. And so I want you to think about the types of fuels that you're aware of that we run our internal combustion engines on. The ones that should be obvious would be gasoline and diesel. Those ones you see at the pump all the time. The one that you see at the pump more often now is called ethanol. So ethanol is a type of alcohol, and ethanol is actually the type of alcohol that is drinking alcohol. So that's a type of alcohol. We also run on another type of fuel that's called methanol, which is a different type of alcohol, but it is not the drinking alcohol. Other fuels. So hopefully you're saying other fuels like propane, natural gas. I don't know why I'm drawing a blank, but propane and natural gas. Then some of the other ones that we have would be compressed natural gas, CNG, LPG for propane, and gasoline, diesel, methanol, ethanol. There's some of you might even be going out to like French fry oil or things like that, and in diesels we can run them on those types of fuels as well. But those would be common types of fuels, at least, that we run. In racing, they'll also use another type of fuel that's called nitro. But all of these fuels that we're using in these in our engines, internal combustion engines, they're all a hydrocarbon-based fuel, so there's a different composition of hydrogen and carbon for all the different fuels that we use, including things even like butane and so forth. But the point of this is there's energy that's stored in fuel. And so energy is not created or destroyed, it only changes form, but there's an energy that's stored in fuel that's a chemical energy. And then when we burn it, then that's converted into heat energy, and that heat is trapped in a confined space, and so it puts pressure on that piston, and we convert that to mechanical energy, which we ultimately use to propel the car down the road. And so the point of these two pictures that are up here is these are our common drivetrains. That we have one here that is rear wheel drive, and this one which is a common configuration for front wheel drive. And so the engine that we have in our engine is our power source to propel the vehicle down the road and to operate all the accessories and everything else that we do. We can use this internal combustion engine to run on a variety of different types of fuels and make power for us. And so to start out, we'll start up here at the top, and in that top picture, then A is the engine. So that's our power plant that we have there. And then C is going to be our transmission. And then B there is a clutch. So then what type of, B is the clutch. So what type of transmission would this be? Manual transmission. So manual transmissions have a clutch. An automatic transmission connecting our engine to our transmission would have a torque converter that uses fluid coupling to be able to connect our engine to our transmission, to transmit the power from the engine to the rest of the drivetrain. Then moving further down, D would be the propeller shaft, as it's listed in the picture. Another name for that would be drive line or drive shaft is another common term for those, and those are all proper names there. And then F will be the differential. So the differential is what takes everything from the engine rotates on a plane like this, that we have it all rotating this way. It rotates through the rest of the drivetrain, the transmission, and then the drive shaft. When it gets here, this is the pinion gear, the one that looks like a little triangle right there. That's the pinion gear, and that mates up to a ring gear. And they mate up at 90 degrees to each other. And so this differential turns the rotation this way 90 degrees to where we have it rotating down the same plane that the tires and wheels would rotate. And we transfer that force and that rotating force, which we refer to actually as torque, and that gets transferred out to the wheels by the axles. And so our rear axle shaft is G, and then the axle housing is just the case around that holds all of those internal parts, and that would be E. Then moving down below to the lower picture there, we have a typical front wheel drive configuration. It's not that this configuration couldn't be put in the rear of cars. Some vehicles do mount up a configuration like this that would be in the rear. And some of those would include vehicles like Volkswagen in their old Bugs, the MR2 Spider, Pontiac Fiero, the Porsche 911 Porsche, things like that. And some, maybe you can think of some others that have that are rear engine in that regard, and some of your supercars and things are that way as well. So moving on, A is still the engine, all right, and B is still the clutch, but C is now something different. And so C is referred to as a transaxle. And so what they've done is they've combined the transmission and the differential into one housing. And you can see those. There's our transmission, there's the differential. This is still a manual transmission since it has a clutch. But what did they get rid of when they combined that transmission and differential? The propeller shaft, or the drive shaft, or drive line. And so that gets eliminated on a front wheel drive configuration. And so now we still have our differential, which is still F. Then now we have a different type of axle that is, the drive axle is E, but we have a different type of axle and joint where at D, which is called a CV joint. And a CV joint is just a movable connection that, just like kind of like your wrist, it can rotate in all directions like that. And that enables us to be on a front wheel drive and have the wheels be able to turn and still transmit power, move up and down with the drive, and still transmit power as the suspension allows the wheels to travel and keep the tires planted on the ground. So that's a couple of our drivetrain configurations that we have. Power is originating at the engine and then will be transmitted out to those wheels. So I want to square that up so I don't drive anybody crazy. This is a few different block configurations and engine configurations, the oldest of which and the earliest style would be our inline style. And this is an inline style of configuration. We know that this would be an inline 4 because we can see that there are 4 pistons. So there's our pistons and connecting rods on the crankshaft. And so that would show an inline 4 configuration there. Then this, and before I leave that, I want to say that's our earliest style. They started out with inline motors. They had inline 4s, and then when they wanted more power, they would add cylinders to that. And so an inline 6, and then if they wanted more power, they'd add more cylinders, inline 8, and there's inline 8, 10, 12 even motors that were inline, that every time they wanted to produce more power, they added cylinders in line. And so that's from kind of the generation of the 30s that you would see the cars that they had a real long hood line to house a real long inline motor in that regard. And so they kind of, all the Dick Tracy kind of era, if you're familiar with some of that. So inline motors that way, early style of motor, inline, then somebody somewhere along the line said, well, why do we keep stacking them like this? Why don't we just go like this? And then that produced what we would refer to as a V motor, or a V. This one is a V6 because it also has 6 pistons. And so our inline is A, our V6 is B, and then C is now a V8, and we can tell that it's a V8 because it has 1, 2, 3, 4, 5, 6, 7, 8 cylinders. So now you see the 8 cylinders in the engine block. And so one of the things that you'll notice is on an engine like this, you'll see that they physically could not put a connecting rod in the same spot as the other. And so on a V motor, there's always one cylinder that's out in front. They don't perfectly, if these were my cylinders, they would never perfectly line up and be perfectly square to each other. They all have to be offset, just like you would lace your fingers together like this. And so in that case, on any V motor, there's always a cylinder that is out in front, just like if I lace my fingers together, I'll have a pinky that's out in front of the other, or a pointer finger that's out in front of the other. There's always a cylinder that's out in front of the other, at least by the width of a connecting rod. So a connecting rod like that, because they can't physically mount it to the same place as a journal. And so whenever I'm looking at any V motor and I want to know where number 1 cylinder is, number 1 cylinder will be the furthest cylinder to the front. And if you look down the side of any V motor, you'll actually see that one cylinder head will always lead the other by at least the width of a connecting rod. It has to do with the fact that the cylinder head covers the cylinders, and the cylinders have to be offset because of how the connecting rods are connected to that crankshaft. So there's our V8, and we know it's a V8 because we can see the bores in the block. So 8 bores in the block, or cylinders in the block. So that's C. Then we get around to this style of motor, which is a opposed. Some of you may know it as a Boxer motor, named after the man that invented it. German engineering there. Boxer motor or opposed motor. And an opposed motor, you'll have the pistons move out at the same time and then in at the same time. What's a manufacturer that often uses this opposed motor? Subaru was one. They still use it today. That's the motor that they use. And then you'll see this also in Porsche. You see it also in the older Volkswagens and so forth. So that's your opposed motor there. Still internal combustion engine. That's D. And then E would be our rotary, process of elimination. You see those in the RX-7s, RX-8s. Still a 4-stroke cycle engine, intake, compression, power, exhaust. couple of things that I want to point out that I have that I want to point out while we're here on this picture. So you'll notice, and we've had the conversation about companion cylinders, that there's 2 pistons that are up and 2 pistons that are down in this picture, and that's typical with any even numbered cylinder motor. So anytime you have 4, 6, 8, 10, 12 cylinder motors, they're going to design them to have companion cylinders because of balance. So as those 2 pistons go up, then the other 2 pistons are going down. That provides balance to that engine. You'll also see that as this piston is up, its counterweight is down, so that also provides balance to these engines. Engines with even number cylinders tend to run smoother than engines with odd number cylinders motors, and so the even numbered cylinders are naturally balanced. Odd numbered cylinders like your inline 3, they're making inline 5, engines like that tend to naturally be out of balance. To counteract that, a lot of manufacturers would actually put in another component called a balance shaft. It'll kind of have an S-curve to it. Balance shafts in motors will help them to run smoother and shake less because they're out of balance. That's especially important on engines that are odd numbered cylinders. I think I've mentioned to this class, but I may not have, about how poorly it looks like the little 1 liter Geo Metro motor runs. It's an inline 3. First time I worked on one of those, I'm like, oh my gosh, we're gonna have to fix how that freaking thing runs. And then I realized, like, that's how it runs. It didn't have any problems with its running condition, and it wasn't misfiring, although that motor was shaking all over the place. And so even number cylinders tend to run smoother than your odd numbered cylinders. With engines with companion cylinders, just as an example, if the firing order of this motor in most 4 cylinders is 1, 3, 4, 2. And to be able to determine which cylinders are companion cylinders, you would take that firing order and cut it in half. And so if we said 1 and 3, 4 and 2, then 1 and 4 would be companion cylinders and 3 and 2 would be companion cylinders. And I'm realizing as I said this that I didn't describe what a firing order means. A firing order, and saying that our firing order is 1, 3, 4, 2, is referring to the order in which power strokes occur. And so we would have a power stroke that would occur here on this one. So 1, and then number 3 would have its power stroke next, and then number 4 would have its power stroke next, and then number 2. And so that's the order in which power strokes occur in an engine. We can see that from this firing order for this 4-cylinder, 1 and 4 would be companion cylinders. So companion cylinders in this regard, if both pistons are up like it's shown in this picture, then we could say that number 1 would be coming down on an intake stroke while number 4 is coming down on a power stroke. And then while number 1 is coming up on a compression stroke, number 4 would be coming up on an exhaust stroke. And then as number 1 comes down on a power stroke, then number 4 would be coming down on an intake stroke. And as number 1 comes up on its exhaust stroke, then number 4 would be coming up on a compression stroke. And so with companion cylinders, what you have is you have pistons that are making the same movement, but they're on different strokes. So moving on to the next picture here, try to square this guy up. This is now looking at different valve train configurations. And so we've got a variety of different valve train configurations that we can use and that are used on internal combustion engines. And so the oldest of which, an early design, it would be of at least what's on the board, is what we would refer to as cam in block. Sometimes you'll hear this referred to as OHV. So OHV for overhead valve, because the valves are above the piston there. Or sometimes the slang in the industry is to refer to this as a push rod motor, because this has push rods here and the others do not. Earlier than this, they had the valves in the block, and you would see that with flathead motors. So those are quite old, in the 40s and before that. I don't know if they used them in the 50s or not. But I think they started getting phased out. There maybe was manufacturers that used them in the 50s. Ask Mr. Posey. But this would be our overhead valve configuration, push rod motor or cam and block, because the cam is in the block. Then moving from there, this configuration is our overhead cam, or OHC. A lot of times you would hear this called SOHC, for single overhead cam. So, and then in this configuration, now we have eliminated a lot of the drivetrain. The valve train, I should say. We've eliminated in a lot of cases, the push rod. We've eliminated the lifters, and so now we have the cam up overhead closer to the valves where it would operate them. And so this is an increase in efficiency and getting rid of weight in that valve train. And so it has the effect then of making that motor more responsive. Now, and because it's closer to the components it operates, and there's less parts to wear out at that point. Then we move to a dual overhead cam, DOHC in this case. And so now in this valve train configuration, we'll have a camshaft that will operate the intake valves and a camshaft that would operate the exhaust valves. And so this also freed up a lot of these motors and improved their breathing, because on any of these designs where the valves were located on the same side, the air-fuel mixture had to come into the motor, make a U-turn, and come out, right? Where with the valve train design that we can get away with on a dual overhead cam, the air would come into the motor and then flow out the other side. And so it flows a lot better, breathes a lot better, performance is better, efficiency of those motors is better, and it enables a lot more sophisticated design. This is also what led to a lot of the advent of being able to have variable valve timing, where they can change the sprockets on here and accommodate one that is not fixed like those, but that can be re-indexed to the camshaft. And they use hydraulics to do that, or oil pressure to do that, because fluids don't compress. So they'll have a chamber inside that sprocket where they can re-index it by filling a chamber with oil, and once they fill it with oil, then it's fixed and solid, and they can change the valve timing. If they want the exhaust valve to open a little sooner, they can advance that cam. If they want the intake valve to stay open longer, they can advance that cam. So provides what we see with variable valve timing in that regard. I want to point out a couple other things in this diagram while we have it up here. This one, there's different ways that we can connect the camshaft to the crankshaft. It's always a 2-to-1 ratio, right? So 2 rotations of the crank to every 1 rotation of the cam. But in this diagram like this, we can see that this camshaft and crankshaft is connected with a rubber belt or a timing belt. This requires maintenance as a serviceable item. We've talked about having to look up and schedule maintenance on when timing belts should be changed. This one is a chain motor, to where it's in most cases, all cases with chain motors, they're considered a lifetime component, where we don't go after them and do any repairs to them unless there is a problem with it. And so this cam is connected to the crankshaft with a chain. Then on this design, it's gear to gear. So they put the gears and mesh the gears directly together in this cam and block. And it's a neat sound. If you ever get around any older cars that are gear to gear, you can hear the gears meshing, where chains and belts are quieter. All right. So I don't think there's anything else that I want to say on this one. So next I want to talk about just some of the names of the parts that we'll use for an internal combustion engine, get some of the vocabulary down. The design that you see up here kind of looks at like what we would call a hemispherical design, but this is a modern combustion chamber design that is referred to as a Pentrith design. This would be a dual overhead cam motor where we can see that we've got our, cam lobes here on either side, one for our intake or one for the exhaust. So we'll go ahead and look at the components and main components and names that we have here. So the crankshaft on this would be H. So that's our crankshaft. That the piston connects to the crankshaft, and we always want to associate that the crankshaft is associated with the pistons, and then the camshaft is associated with the valves. Then with our block, what F right here is actually the block. B for block. So F is the block. And it's more than just what it's pointing to there. This is kind of the bottom end of the block, but our block goes all the way up to there at C, which C is the head gasket. So then the cylinder head is A, and the cylinder head is this whole area up here. This all we would refer to in a big metal chunk there. We would refer to the cylinder head, and the cylinder head obviously seals off the cylinder bore in the block. And then is where our combustion chamber is located, where our spark plug right down the middle. So this area below the cylinder head and above the piston, we would refer to as the combustion chamber. And when the piston is all the way up at top dead center, we're squeezing down that air fuel mixture down into its smallest volume, then that is literally our combustion chamber there. The rings on the piston would be D. Typically with rings, we'll have 2 compression rings and 1 oil control ring, so a grand total of 3 rings. The compression rings are 1 piece. The oil control ring is a 3-piece ring. What its job is that we splash lubricate the cylinder wall as the crankshaft rotates down into the oil that'll be down in the oil pan. It'll sling oil up underneath the piston and lubricate the cylinder walls. The oil control ring will scrape off excess oil and it'll drip back down into the oil pan. Then our port would be B, valve port there. The connecting rod is G. The couple of things that I wanted to point out to you on this overhead design. This is not a rocker. This we would typically refer to as a follower. It kind of serves the job as a rocker, but it's kind of an intermediate in between the cam lobe there and our valve. This would be a little lifter off to the side there to help maintain proper clearance and tension so that we don't have parts that can rattle around. But that we would typically refer to as a follower on this overhead design. So then looking at our bottom end and components here on the bottom end of this, bottom end components are crankshaft, which we connect our pistons and connecting rods to. That would be C. Then the piston itself is J. Then if I move down to what I would be our connecting rod. Then typically the little hole that's right there on the piston, that would be what would be called the wrist pin, and that's what pins the connecting rod to the piston head. Then our timing sprockets connecting our cam to our crank would be, or sprockets that allow our chain to connect our cam to our crank would be G. Then the timing chain, F. Our camshaft itself, H. Then the main bearings that would be the support bearings that would be the bearing support that would be the bearings that end up holding our piston or our crankshaft in place, and then reduce friction as that crankshaft is bolted up into the block. Those bearings would be E, and typically with bearings we'll have one special bearing that would be called a thrust bearing, and it'll have shoulders on it. I've shown you that in one of the other videos, and that prevents in play of this crank being able to slide back and forth. A lot of times they can put that thrust bearing anywhere, but a lot of times they're towards the back, although some motors will put it in the middle. Main bearings and main caps Main bearings are E, and the main caps would be D. One point that I just wanted to make is that in one of the other pictures early on in the class, we talked about 4-bolt mains. This would be a 2-bolt main. What you would notice on those 4-bolt mains is they typically only had 4 bolts towards the middle because that's where you need the most reinforcement. If you have any long component, it tends to bow in the middle, and so they tend to reinforce in the middle with 4-bolt mains. Cylinder block is A, and then our oil pump is B over here. So that's our oil pump there. A lot of times oil pumps are going to be driven by the cam in a configuration like this. This would stab up through the back of the block. You have a distributor that would come down and tie into that. The distributor distributes spark on that motor, and it moves mechanically, and the distributor is tied into a gear or sprocket that would be on the cam. And so since the distributor is turning and the oil pump is tied into the distributor, then that would turn the oil pump as well. It's not uncommon on a lot of modern motors to have a little cog on the front of the crank, and they'll bolt the oil pump up to the front of the crank so that when the crank turns, it also drives the oil pump. So this is a view of our 4-stroke cycle. And so one of the things that I want you to key in on looking at this view is that we can tell what stroke it is by what valves are open or not open, open or closed, and by which direction the piston is moving. And so our 4-stroke cycle in order again is intake, compression, power, exhaust. That's always the order for that 4-stroke cycle. And so if we look on here, we would expect, I want you to identify the intake stroke, compression stroke, power, exhaust stroke. And I want to give you a little bit of time to be able to do that and think. So I would recommend at this point that you pause the movie and then figure out which ones you think are the 4-stroke cycle, and then we'll go ahead and go over it. So spoiler alert, I'm going to cover it now. So our intake stroke, we would expect the piston to be moving down and the intake valve to be open. And so on here, the piston's moving down there, the piston's moving down there, but on our intake stroke, we would have the piston moving down and a valve open, and so B will be our intake stroke. Then on the compression stroke, we expect the piston to then be moving up and for both valves to be closed. And so on this one, the piston is moving up, both valves are closed, so that would be D for our compression stroke. On the power stroke, we expect the piston to be moving down and both valves to be closed, and so A would be our power stroke, and we're also seeing on A that it's showing that there's a spark that's occurring. The reality is that the spark actually occurs on the compression stroke on all of these engines, and the reason for that is fuel takes time to burn. And so we want maximum pressure on the piston just after it peaks over on the power stroke. And since it takes time for fuel to burn, then usually we lead it and start lighting off that air-fuel mixture a little bit before, and so therefore it would occur on the compression stroke. Spark would occur on the compression stroke. Then on our exhaust stroke, we expect the piston to be moving up and the exhaust valve to be open. So on this one, the piston's moving up and we've got a valve that's open. So C would be the exhaust stroke. Now, I want to give you a point of definition as we go through this, that I want to give you a definition of a misfire. And so I'll write this over on the side, and I suggest that you commit this to memory. But a misfire is a cylinder that does not make power on the power stroke. So a cylinder that doesn't make power on the power stroke, or a cylinder that doesn't contribute to making power for that engine, we would refer to as a misfiring cylinder. So that's our definition of a misfire. Misfires on modern vehicles, 96 and newer, the computer controlled system is tracking and looking for misfires, it'll turn your check engine light on. If you ever have a check engine light that's flashing or blinking at you while you're driving on your car, you should pull your car over and not continue to drive it like that and fix it immediately, because a misfire would damage an expensive component in your exhaust called the catalytic converter, and so we don't want to drive our cars around with a misfire. So check engine light that comes on is an emissions failure, period. Check engine light that is blinking at you is a catalyst damaging misfire. That's what that's supposed to indicate. And so anything that affects our 4-stroke cycle would cause a misfire. And so what are some of the things that you're familiar with that cause misfires? Usually the first answer that I tend to get is bad spark plugs, or something ignition system related. And you're exactly right. So if I had spark that did not occur, just in general, right? If I have spark that doesn't occur and I don't light the air fuel mixture, what stroke does that affect? So that would affect my power stroke, literally, all right? And so if I do not have spark that occurs, that will affect my power stroke. So next, if I have a mechanical failure and I can't make compression, then obviously that affects my compression stroke. And so my compression stroke, I have to be able to compact that air fuel mixture down into a small volume. And so if we have this as a rule, and I've mentioned this, I always mention this to all my classes, this is the rule. If I cannot compress the air fuel mixture, I cannot light it. And so if that air fuel mixture is not compressed on my compression stroke, then I cannot light it, and therefore I end up having a misfire again. Now, if on the intake stroke, I'm supposed to be pulling in an air fuel mixture, but if I don't have any fuel, if no fuel is sprayed by that injector or something along those lines, then in that case, I just pull in air, I compress air, I try to light it, there's nothing to light. Therefore, I have a misfire that affects my power stroke again. But that's something that relates to the job of my intake stroke. My intake stroke is supposed to pull in an air fuel mixture, all right? So then, what if I had plugged exhaust? If I had plugged exhaust and so I have a normal intake stroke, pull in an air fuel mixture, and then I compress it, fine. I light it, burn that air fuel mixture. Then I come around on the exhaust stroke and I cannot get rid of it. Therefore, that burned exhaust gas stays in the cylinder and occupies that space. Then I turn around and try to pull in an air fuel mixture and I can't because the space is already occupied. That's something that would then affect my exhaust stroke. If I can't get rid of the exhaust and I have plugged exhaust, another way that can happen is if the cam goes flat. So that cam's supposed to have a nice peak that would roll around and push open an intake valve. If it turns into a nice perfect circle, then it doesn't open the intake valve. Or if it turns into a perfect circle on the exhaust cam lobe, then it doesn't open the exhaust valve. Then my motor can't breathe. That ultimately affects the 4-stroke cycle and causes a misfire as well. So anything that affects my 4-stroke cycle is going to ultimately result in a misfire. So I want to make sure that you can see this well as we go over this. And so this is just a simple table that is in this handout, but what it represents is this represents 2 revolutions of the crankshaft for a 4-cylinder motor. And so they're identifying that there's our first cylinder, our second cylinder, third cylinder, fourth cylinder. And then we know that a rotation in terms of degrees of a crankshaft is a full circle is 360 degrees. So 360 degrees there, and then that would, in 1 revolution of the crank, we complete 2 strokes. And so a stroke is 180 degrees of crankshaft rotation, or half a turn of the crank. And so this represents our 4-stroke cycle, right? 1, 2, 3, 4 strokes for this cylinder, right? 1, 2, 3, 4 strokes there. And so, but it requires 2 revolutions of the crankshaft to complete 4 strokes. So in 2 revolutions, 1 revolution there, 1 revolution there, altogether that is 720 degrees. But there's our first stroke, second stroke, third stroke, fourth stroke. And so in 1 revolution of the crankshaft, we complete 2 strokes, right? First 2 strokes in the first revolution, second 2 strokes in our second revolution to complete a grand total of our 4 strokes. So the 4-stroke cycle always occurs in order. And so as we go over this, I'm just going to kind of go over it and we'll fill in the blanks a little bit later. But if we start out for our first cylinder like this, it goes intake, compression, power, exhaust. Then on this one, intake, compression, power, exhaust. Blank, compression, power, exhaust. This would be intake. Then intake, blank, power, exhaust. This would be compression. And so the answer to C would be 180, right? A stroke is 180 degrees. Now, a couple of things that I want you to appreciate about this. Now, this one has a power stroke there, right? And so in this 2 revolutions of the crank, we complete a power stroke for every single cylinder in this motor. This one has a power stroke here. This second cylinder has a power stroke there. Third cylinder has a power stroke there. Fourth cylinder has a power stroke there. And on a 4-cylinder motor, then we can see that on a 4-cylinder, a stroke is 180 degrees. And if we took our 720 degrees and divided it by 4, then we get our ignition interval. And so our ignition interval, 720 divided by 4, also equals 180. And so on a 4-cylinder motor, then we basically do not have power strokes that ever overlap. All right, but if you took your 720 and divided it by 8 for a V8 motor, then you start to have power strokes that overlap. But on a 4-cylinder motor, 4-stroke cycle, we do have continuous power strokes. But when the power stroke ends for this one, then this one begins. Then the power stroke ends for that one, then this one begins, ends for that one, this one begins. And also on a 4-cylinder motor, at any given time, that 4-stroke cycle is always represented. While this one's on a power, this one's on a compression, this one's on an intake, and that one's on an exhaust. And the same is true at any given moment. All 4 strokes of our 4-stroke cycle are always represented. So now we basically covered this stuff here, all right? And now we want to talk, I want to talk a little bit about some of the other math. I want you to appreciate how quickly everything happens on this engine. And so doing some of the math will do that. I also want to say before we leave this diagram that for a 4-stroke cycle engine, no matter how many cylinders it has, that principle is true, that when we complete 2 revolutions of the crankshaft, we'll complete a 4-stroke cycle in every single cylinder on that motor. And so if that's a V8 engine, same is true. 2 revolutions complete a 4-stroke cycle in every single cylinder on that motor. So moving on down here to these lower questions. So on here, it says a revolution is how many degrees of crankshaft rotation. And in 1 revolution, we complete 360 degrees. The camshaft rotates blank degrees during a 4-stroke cycle. Now, I want to remind you in this regard that it is a 2-to-1 ratio, right? 2-to-1 ratio like that. So that means that that is 2 revolutions of the crank to 1 revolution of the cam. So in our 4-stroke cycle, the crank's going to rotate twice, but the cam will rotate once, which 1 revolution is 360. The crankshaft rotates how many degrees during our 4-stroke cycle? The answer to that will be 720. So the crankshaft rotates 720 degrees in our 4-stroke cycle. Then we get down to this math, and it says, for question number 4, how many revolutions does the crankshaft make per second at 3,000 RPMs? So we're going to cross multiply and come up with our formula. So if we have 3,000 revolutions per 1 minute. That's how we would write that mathematically. And then in 1 minute, we have 60 seconds. So if we cross multiply, these cancel. So then I get 3,000 divided by 60. And then that will give me revolutions per second. So the revolutions there and the seconds there. So 3,000 divided by 60 gives me 50 revolutions per second. So the answer to that, would be how many revolutions does the crankshaft make per second at 3,000 RPMs? The answer to that is 50 revolutions. Then at 3,000 RPMs, how many times does each intake valve open in a minute? So, if we come back up and we look at our diagram up here, I'll try not to make you dizzy with this. I have my pointer still there. So if we come up and we look at our diagram, then on here, I'm going to pull that down a little bit so that we can see. So on here, if we look at this one, because it's in order, bump my table there. If we look at this one is going to be in order. So I have intake, compression, power, exhaust. So we know that in our 4-stroke cycle, it takes 2 revolutions of the crankshaft. We have 1 revolution here, 1 revolution here. And if we just look at this 3rd cylinder, right, we know that the intake valve would open on the intake stroke. So on this revolution of the crank, the intake valve opened, but on this revolution of the crank, it did not. So the intake valve would only open every other revolution, right? So in that case, if it opens every other revolution, then in 3,000 full revolutions, it would open every other revolution. So that's half the time. So 3,000 divided by 2 would give me 1,500. So in 1 minute, at 3,000 RPMs, that intake valve would open 1,500 times. Pretty impressive. So then, if we come and answer question number 6, at 3,000 RPMs, how many times does each intake valve open in 1 second? So if we already know that the from here, how many revolutions does the crankshaft make in a second? If it makes 50 revolutions, and then we take a look up at our diagram and we say, okay, every other revolution completes a 4-stroke cycle, right? It takes 2 of these revolutions to complete a 4-stroke cycle. So then that means every other revolution completes a 4-stroke cycle of that 50. Then that means that that the intake valve would have opened on this revolution, but not on this one. And so in that case, we're going to take our 50 and divide it by 2. We already did the math to complete how many revolutions occur at 3,000 RPMs. Then we'll take our 50 and divide it by 2, which means that that intake valve opens 25 times per second. Then at 3,000 RPMs, how many times does each exhaust valve open in a minute? Exhaust valves open again, just like an intake. Exhaust valve opened here on the exhaust stroke, but not on this revolution. So this one, not that one, every other revolution. So then again, in a minute, that is 1,500. And then how many times does the exhaust valve open in a second? Every other revolution. We have 50 revolutions per second at 3,000 RPM. So every other revolution there is again 25. Then how many 4-stroke cycles occur in a minute? For a cylinder, that's again in a minute is 1,500. And then how many 4-stroke cycles occur a second in a cylinder? That again is 25. Now, I want to come back up to this diagram. I'm going to try not to make you guys dizzy in doing so, so I apologize. But I want to say this. The intake valve at 3,000 RPMs opens 25 times a second. So we have 25 intake strokes that occur a second. We have, at 3,000 RPMs, we would have 25 compression strokes that occur a second, 25 power strokes a second, 25 exhaust strokes a second per cylinder. So that's for one cylinder. So if we're talking about a whole motor that has multiple cylinders, we would have 25 power strokes that occur per second, all right? But that is, if we have 25 4-stroke cycles that occur for that whole motor, then that is 25 for this cylinder, 25 power strokes for this cylinder, 25 for this one, 25 for this one, and 25 for that one. And so for a 4-cylinder motor at 3,000 RPMs, that means that we have 100 power strokes per second that occur. That's a 4-banger, right? If you went and took that and extrapolate that out to a V8, then that means at 3,000 RPMs for a V8, twice the number of cylinders, twice the power strokes, we would have 200 power strokes a second on a V8. 3,000 RPMs is not the maximum RPM that we would run our motors at. A lot of motors, just for easy math, they're going to have a red line, the max rev limit, somewhere around on their tach. The max rev limit that they recommend that you rev a motor up to somewhere on their tach at about 6,000 RPMs. And so for a V8 engine, if we double those numbers, that becomes 400 power strokes a second for the whole engine. Now, pretty impressive. If you start doing Formula One will rev 18,000 RPMs, 20,000 RPMs. You go ahead and do the math. That's a lot of power strokes. That's a lot of intake strokes. That's a lot of compression strokes and exhaust strokes. And not to mention, on a piston engine, consider the fact that for these strokes, that piston has to come up to top dead center, come to a dead stop, turn around, go back to bottom dead center, come to a dead stop, come back up to top dead center, dead stop, go back down to bottom dead center, and it comes to a stop and then moves back and forth. It is moving back and forth this whole time. Now, I want you to appreciate how quickly all of this happens. That when we have our 4-stroke cycle occurring and we have at 6,000 RPMs, which is not an unreasonable RPM for a 4-stroke cycle internal combustion engine, that we, on a V8, we have 400 power strokes a second. Everything is happening super fast. Down to idle, we have 4 to 5 power strokes per second that are happening per cylinder at idle. So when you learn to appreciate how quickly everything has to happen with these engines and how quickly things are happening with these motors, then it becomes pretty easy to understand how some seemingly minor problem starts to become a major drivability issue or major running problem that didn't fire number one cylinder. Boom, you feel it because it's expecting, or we need 25 power strokes a second per cylinder, 25 sparks per second per cylinder at just 3,000 RPMs. That's 50 sparks per second per cylinder at 6,000 RPMs. So hopefully this little exercise in doing some of the math helps you appreciate how fine-tuned a mechanical machine that these engines actually are and how quickly everything has to happen and how some minor problem can cause a drastic running problem on a car because of how quickly everything has to happen. Air's got to get into the cylinder and with fuel with it. We got to compress it. We got to light it. We got to get rid of it very, very quickly on these engines. So hopefully that helps you appreciate that.